Welcome back to The Explainer. Today, we are going on a really incredible microscopic to macroscopic journey. We're going to track exactly how toxins and poisons interact with the human body, and we're covering Lesson 13 today, pulling crucial insights from chapters 12 through 15 of our source material. That means we're looking at chemical, biochemical, neuro, and withdrawal principles. We're starting from the tiniest atomic clashes and building all the way up to complex, full-body clinical withdrawal syndromes. Because, to truly grasp toxicology, we can't just memorize symptoms. We actually need to uncover the fundamental chemical and biological rules of the game.
Okay, let's dive into this. Here is our roadmap for today. We're going to cover 4 main areas. First, toxic chemistry and molecules. Second, disrupting biochemical metabolic processes. Third, hijacking the nervous system. And finally, fourth, the physiology of withdrawal.
Before we get into the heavy chemistry, let's formally introduce our invader for this journey. In the toxicology world, this invader is known as a xenobiotic. Now, a xenobiotic is basically just a compound that is completely foreign to a living system. When it sneaks into the body, it can cause some serious injury by messing with our critical metabolic processes, damaging our cellular structural integrity, or literally altering our genetic material. To really understand poisoning, we have to first understand how these xenobiotics speak the body's molecular language.
So let's jump right into Section 1, Toxic Chemistry and Molecules. Welcome to the atomic battlefield.
Believe it or not, a huge portion of organic reactions in toxicology ultimately boil down to a microscopic game of tag, a relentless atomic hunt between nucleophiles and electrophiles. Nucleophiles are nucleus-loving. They have an increased electron density, meaning they've got extra electrons to share. Think of toxins like cyanide or carbon monoxide. Because they're loaded with electrons, they are naturally drawn to electrophiles, which are electron-loving because they are electron deficient. When a nucleophile hunts down and reacts with an electrophile, electrons shift, bonds break or form, and, well, toxicological damage is usually the result.
Now, what's really interesting here is how these tiny, seemingly simple atomic interactions can create such massive cellular devastation. Take the Fenton and Haber-Weiss reactions. They illustrate how hydrogen peroxide interacts with transition metals, like iron, to pump out highly reactive hydroxyl radicals. You can think of these reactive oxygen species as cellular wrecking balls. The most consequential damage they do is to the cell membrane itself. They kick off this lipid peroxidative cascade, which literally tears apart the lipid membranes until the cell is utterly destroyed. It's brutal. It's honestly wild to see what happens when our body's natural defenses get completely overwhelmed. Let's look at the toxic acetaminophen metabolite, known as NAPQ. Normally, our body has its own built-in bodyguard, a fantastic antioxidant, reducing agent, and nucleophile called glutathione that safely traps these reactive species. But if you take an overdose and that glutathione gets depleted, that's when the trouble starts. The electron-deficient NAPQ goes rogue, acting as a destructive electrophile. It attacks the cysteine residues on our liver proteins, forms covalent bonds, and leads to severe liver cell damage.
Let's move to Section 2 and see how this builds. Disrupting biochemical metabolic processes, halting the cellular engine. Every single cell in your body is essentially a tiny engine, and that engine runs on high-energy phosphate bonds, mostly in the form of ATP. ATP is the fuel. It powers cellular synthesis, active transport, electrolyte balance, and keeps those vital membranes intact. So, when a xenobiotic comes along and inhibits the production or use of ATP, it is literally like cutting the power grid to an entire city. Without that energy, all these absolutely crucial cellular processes just rapidly fail, leading straight to cell dysfunction and death.
A really fascinating example of this kind of metabolic disruption involves toxic alcohols, specifically methanol and ethylene glycol. Here's the twist. The compounds themselves actually aren't all that toxic directly. They mostly just cause inebriation, kind of like regular drinking alcohol. The real danger? It's in their metabolic pathways. When they get metabolized by an enzyme called alcohol dehydrogenase, methanol turns into highly toxic formaldehyde and formic acid, which causes severe retinal injury and even blindness. Ethylene glycol, on the other hand, is turned into glyoxylic acid and oxalic acid, which literally precipitate as sharp crystals in your renal tubules, destroying the kidneys. So the poison isn't the alcohol itself, it's what our own cellular engines turn it into. No way, right?
But here is exactly where toxicology fights back. If that enzyme, alcohol dehydrogenase, is the bad guy creating the toxic metabolites, we can actually bypass the poison's effect by blocking the enzyme itself. An antidote like fomepizole acts as a competitive inhibitor. It sneaks in and binds directly to the active site of that enzyme. Because it's competing with the toxic alcohol for that exact same spot, the body needs much higher concentrations of the substrate to reach half the maximum reaction rate. Now, the maximum reaction rate itself doesn't change, but by increasing that apparent Km, fomepizole essentially buys us precious time and stops the creation of those deadly metabolites. It's a real game changer.
All right, moving into Act 3, hijacking the nervous system, hacking communication. I want you to visualize the human nervous system as a highly delicate physical scale. On one side, you've got your excitatory impulses, and on the other side, your inhibitory impulses. Up in the central nervous system, excitatory neurons want to fire constantly, but inhibitory neurons are always there keeping them in check. Whenever you need to take an action, that inhibitory tone just momentarily lifts. Essentially, all human neurophysiology relies on the incredibly careful, precise disinhibition of these impulses.
So the crucial point is how different substances interact with this scale. Notice how our chief inhibitory transmitters, like GABA and glycine, the brakes, are heavily affected by sedating xenobiotics like ethanol. Then we have our primary excitatory transmitter, glutamate, the gas pedal, acting on NMDA receptors. And finally, we have modulatory transmitters like dopamine and serotonin, which are heavily influenced by stimulants like amphetamines and cocaine. Toxins cause their profound full-body effects by either mimicking, enhancing, or outright blocking these specific chemical messengers.
But how exactly do they tip the scale? Well, they don't just passively float around hoping for the best, they actively hack the synapse. Some of them use direct receptor interaction. For instance, domoic acid directly stimulates excitatory AMPA receptors, while antimuscarinic drugs just directly block acetylcholine receptors. Others use enzyme and transporter exploitation. Amphetamines are incredibly sneaky here. They actually get taken up by the presynaptic neurons using the body's very own catecholamine transporters. Once they get inside, they force a massive release of stored catecholamines, completely flooding the brain with excitatory signals.
Which brings us to our final section, the physiology of withdrawal, the aftermath of adaptation.
When a brain is continuously bombarded by an invading xenobiotic, it doesn't just sit back and take it. It adapts, it fights to survive. And clinical withdrawal is actually just the physical manifestation of that survival adaptation. The DSM-4 perfectly grounds this biological theory in clinical reality. It notes that a true withdrawal syndrome requires the continuous presence of a substance just to relieve or prevent symptoms. Simple tolerance? That just means you need a higher dose to feel the same high. But true physiological dependence and withdrawal mean that the constant presence of the xenobiotic is now functionally required to prevent massive systemic dysfunction.
Let's walk through the exact timeline of how this actually happens, step by step. First, you have tonic, continuous stimulation by a xenobiotic. Let's use a depressant as an example. Second, the neuron adapts to survive. Since it's being overly inhibited by the drug, it will downregulate its inhibitory receptors and upregulate its excitatory ones, just to find a new functional baseline. Third, the xenobiotic is suddenly removed. And fourth, because the brain structurally changed its receptor scale to fight that depressant, you are suddenly left with explosive, unchecked excitation. It's like a slingshot letting go.
You might be wondering, how on earth is the brain making these changes? Well, it's not some temporary chemical illusion, it is literal structural remodeling. Toxicology has pinpointed 6 primary mechanisms of neuroadaptation. This includes altering genomic mechanisms via mRNA, activating second messenger systems like CAMP, physically removing receptors from the cell surface via endocytosis, and shifting synaptic localization. These adaptations happen surprisingly fast, and they physically alter the receptor proteins in the brain so fundamentally that the brain now relies on the drug just to function normally.
Bringing all of these concepts together, let's look at a classic example, alcohol withdrawal syndrome. Chronic, heavy alcohol use persistently stimulates the inhibitory GABA-A receptors. The brain responds to this constant suppression by changing its receptor conformations. It downregulates those GABA receptors and upregulates the excitatory NMDA glutamate receptors. When someone abruptly stops drinking, that heavy inhibitory blanket of alcohol is suddenly ripped away. But the brain is still stuck with fewer inhibitory receptors and a ton of extra excitatory ones. The scale aggressively tips, resulting in severe CNS excitation. We're talking tremors, hallucinations, seizures, and massive autonomic stimulation.
We can really cement this concept by contrasting it with opioid withdrawal. Chronic opioid exposure actually decreases the efficacy of the receptor to open potassium channels. In response, the body uses transcription factors to upregulate CAMP-mediated responses, specifically creating way more inward sodium channels just to maintain its basic excitability. When the opioid levels drop, that inward sodium flux happens completely unchecked. This uninhibited activity, primarily at the locus coeruleus in the brain, drives the incredibly painful symptoms of opioid withdrawal: muscle aches, severe nausea, chills. Though, unlike alcohol withdrawal, it is generally not life-threatening.
So what does this all mean for the future? We've seen how toxins dictate terms from the tiny atomic level all the way up to the systemic level, physically rewriting our genomic and receptor landscapes. As our knowledge of these exact genomic adaptations continues to expand, how might we use this molecular map to not just treat the surface symptoms, but to actively reverse addiction and structurally repair the brain at the atomic level? The future of toxicology and addiction medicine is literally hidden right there, in the atoms. Thank you so much for joining me on this deep dive. See you next time.